What do you guys want to eat?
Cornbread!
Of course. I made you cornbread.
Wow, so hot.
It's so hot.
Has this ever happened to you?
Well, if you're a human being, it probably has. With Thanksgiving approaching, most people will be eating foods like turkey, stuffing, and especially cornbread that will almost certainly be served very hot. While many may think that burning their tongue and mouth may just be a minor inconvenience, it can actually have major repercussions, like nerve damage and cancer. So, it is imperative that we find a way to ensure that everyone receives their cornbread at a reasonable temperature within a reasonable time. How can we accomplish this? Well, as chemical engineers, we can use our knowledge of heat transfer to devise a way of cooling the cornbread quickly. A simple way of doing this that doesn't require any device would be to change the size or surface area of the cornbread and determine if that will affect the cornbread's cooling speed. So, why do we want to focus on surface area?
Let's try to predict how the cornbread temperature will change as a function of time and area. Here we have Newton's law of cooling, which states that the amount of heat lost by the cornbread per some amount of time is proportional to the cornbread area times the temperature difference between the surface and the surrounding air. H is the heat transfer coefficient, which is a measure of how well the cornbread is able to lose heat in the air. As we can see, only the heat transfer rate and the temperature of the cornbread are functions of time. Now we have the equation for the total amount of heat that the cornbread loses. This Cp value, the specific heat, represents how resistant the cornbread is to temperature change. Again, we can expect only Q total and the cornbread's temperature to change with time. As a result, we could compare how fast the total heat loss is changing to how fast the temperature changes with time. This is done by re-expressing the right-hand side to give us the equation on the bottom. Now let's do an energy balance on the cornbread upon taking it out of the oven. Simply put, energy in minus energy out must equal the accumulation of energy inside the cornbread. First, we know that there are no energy inputs. Looking at the out term, we saw on the first slide how the cornbread has heat leaving via Newton's law of cooling. Finally, the accumulation, or in this case, the loss of energy in the cornbread equals the final expression from the previous slide. Rewriting the energy balance, we get this equation down below, known as a differential equation. If we solve this differential equation, we end up with this exponential function for temperature here. Let's take a look at this graphically. We can see how as time goes on, the cornbread cools from its initial temperature, here 350 degrees Fahrenheit, to room temperature. As it gets closer to the final temperature, the cooling rate gradually slows down due to the exponential relationship. So how does area specifically impact the temperature change? We have here a video showing what exactly happens when just the cornbread area increases. We can see that as the area increases, the cornbread cools to room temperature faster.
To demonstrate this idea, we can perform a simple experiment. We start by baking cornbread in 3 different pans with different areas. We used 1 full package of Jiffy corn muffin mix for each pan, which is equivalent to about 240 grams. Thus, each cornbread loaf had the same mass but a different surface area. We baked the loaves at 400 degrees Fahrenheit for 15 minutes, and then placed them on a cooling rack in a room at 73 degrees Fahrenheit. We then monitored their temperatures over the course of 9.5 minutes with 30-second intervals using an infrared thermometer gun.
After concluding our experiment and collecting our data, we observed that the temperatures of the cornbread loaves decayed in an exponential manner, similar to our theoretical prediction.
Perhaps more pressing to our situation is how much heat each loaf lost after 9.5 minutes. We can see in this bar graph how the loaf baked in the wide rectangular pan, which had the largest surface area, cooled the largest amount, while the loaf baked in the thin rectangular pan, which had the smallest surface area, cooled the least. This lines up with our hypothesis and theoretical model.
However, we should address 2 issues that occurred during the experiment. First, the wide rectangular cornbread loaf lost a non-negligible amount of its mass when removing it from the pan. As a result, its larger drop in temperature could be partly due to its reduced mass and not just its larger surface area. Still, the circular loaf had a higher surface area and a higher temperature drop than the thin rectangular loaf. Another issue occurred with the IR thermometer measurements, where midway began to display an abrupt increase in temperature. This prevented us from accurately representing the second half of the temperature data. as it no longer followed the exponential trend present with the first half.
The relevance of our experiment also extends beyond the scope of cornbread and safe consumption of foods. Larger surface areas transmitting larger heat rates is an important concept that is applied throughout chemical engineering and beyond. This is best exemplified through the prevalent use of fins, surfaces that extend from the main body of an object. Fins help to substantially increase the heat dissipation through minimal mass increase and are commonly found in space heaters, heat sinks in computer CPUs, and floor heating. Still, our experiment displayed how increasing the surface area of a cornbread loaf allowed it to cool down to a safe temperature quickly, making the cornbread eating experience a little less time-consuming and a little more enjoyable.
That's good!
Looks like a potato.